Hey everybody, welcome back to chemistry. And so today, what I want to do is go over something called Le Chatelier's principle. So when I was in high school, I called this the chandelier principle, but you shouldn't do that. This is Le Chatelier's principle. This is named after a Frenchman who lived in the 1800s who described this principle. So let me tell you a little bit about it. So if I can increase the slide. So Le Chatelier's principle applies to chemical reactions that are reversible and are at equilibrium. But first, you need to know what, in the context of chemistry, a stress is. So a stress is any kind of change of conditions. So you'll often see Le Chatelier's principle expressed in this way. It'll say, if a chemical system is stressed, the system will react in the direction that relieves the stress. Okay, well, here's another way to think of it. It says here, Le Chatelier's principle reworded, if a chemical system undergoes some kind of change of conditions, the system will react in the direction that relieves the change. So what are we going to do is we are going to look at several examples. We're going to see how the following stresses affected equilibrium. So one stress we're going to expose an equilibrium to is increased concentration of reactant or product, and see how that affects the equilibrium. And then maybe another example we'll look at is maybe this time we're decreasing the concentration of reactant or product. Another possibility is that you have a reversible equilibrium, and we're going to see what the effect of increased temperature has on that equilibrium. And then we'll also look at the effect of decreased temperature. And then another possibility is you'll have a reversible equilibrium, and you're looking now at how increasing the pressure affects the equilibrium or decreasing the pressure. So I think the best way to sort of understand Le Chatelier's principle is to do a lot of examples. And so here's my first example, and I'm going to kind of walk you through this. It says, consider the following reversible reaction. And so here, as one reactant, here we have carbon monoxide, and we have 2 moles of that, and it's reacting with the other reactant, which is oxygen, and you produce as a product 2 moles of carbon dioxide. And what I want you to notice is that this is a reversible reaction, so the upper arrow is the forward reaction, and the lower arrow is the reverse reaction. And so we assume in these questions that this is a reaction that is at equilibrium, meaning that the forward reaction is going as fast as the reverse reaction, and the result of that is that the reactants are staying at the same concentration over time, and the product is staying at the same concentration over time. Okay, sounds good. So what we're going to do is we're going to imagine increasing the carbon monoxide concentration like this. Okay, so here's the chemical reaction again. I'm suggesting here that now we're adding more carbon monoxide into the equilibrium. So I'm showing an arrow pointing toward the carbon monoxide. I'm hoping you can sort of read that as to understand that suddenly we're subjecting this equilibrium to a stress, and the stress is increasing the concentration of carbon monoxide. So one of the things we have learned is that if you have a reversible reaction at equilibrium, if you change the concentrations of one of the reactants, then the equilibrium will be disturbed. And so you need to understand what the results are after you disturb the equilibrium with this increased concentration of carbon monoxide. So the way we address that question is we remind ourselves of Le Chatelier's principle, which says this: if you subject a reaction at equilibrium to a stress, the equilibrium will respond in such a way as to relieve the stress. So applied here, if you are increasing the concentration of carbon monoxide, this reaction will change to decrease the concentration of carbon monoxide. So the way it might do that is it might change either the forward reaction or the reverse reaction. So you have to analyze this carefully and ask yourself this question: if I'm increasing the concentration of carbon monoxide, and that is the stress, and the equilibrium responds by wanting to decrease the concentration, do I want to increase the forward reaction, or do I want to increase the reverse reaction? Well, let's think about what the forward reaction might do to the carbon monoxide concentration. if you increase the forward reaction here, what will happen is it will take away carbon monoxide and create carbon dioxide. So yes, if you increase the forward reaction, that should decrease the concentration of carbon monoxide. On the other hand, if you increase reverse reaction, consider what happens. You take some carbon dioxide and you create more carbon monoxide. And so, do you want that to happen? You have increased carbon monoxide as the stress. Do you want to increase the reverse reaction to give you even more carbon monoxide? And the answer is no. So here, if the stress is increased carbon monoxide, what will happen is that this reaction will increase the forward reaction to take the carbon monoxide away. And so the way I indicate that is with this arrow here. And so you can see the forward reaction increases to take the carbon monoxide away. And so one way you can sort of think about it is if you're increasing the carbon monoxide, you're sort of driving the reaction to the right. You're driving it to products. And the way you do that is you increase the forward reaction to be a little bit beyond that of the reverse reaction. So when that happens, you bump the chemical reaction out of equilibrium. So now what I want to answer is, if the stress is increasing carbon monoxide to this reaction and the forward reaction is increasing, I want to understand what happens to the concentration of all these molecules. So the first molecule we want to address is carbon monoxide. Now basically the stress is dumping in more carbon monoxide into this reaction, and so here the carbon monoxide concentration will go up. Okay, sounds good. Now how about the oxygen? That's a little bit trickier to understand. So you're dumping in all this carbon monoxide, but you know that you're going to increase the forward reaction. So that carbon monoxide and the oxygen that is there will be taken away to produce carbon dioxide. So although you're dumping in more carbon monoxide and you temporarily have more carbon monoxide, what happens is the oxygen is being dragged out of the reactants and it's going into the products. So you would expect the oxygen concentration to go down. Now, what would happen to the carbon dioxide concentration? Well, you can see that when you're taking away these reactants and forming products, you're going to get more carbon dioxide, so that should go up. Okay, so we move on to the next example. It says, consider the following reversible reaction. It's the same one we saw before, but imagine decreasing the oxygen concentration like this. And so here, the way I indicate that we are lowering in some fashion the oxygen concentration in this reaction is I'm showing that the oxygen is maybe being taken away out of the reaction by an arrow pointing downward like that. That is the stress, in that we're taking away oxygen from this equilibrium. And so what we have to do is we need to figure out how this reaction responds to the stress. And so here the case is you are here taking away oxygen from the reaction. So what you're going to do is you're either going to increase the forward reaction or the reverse reaction to respond to the stress. You want to increase the oxygen concentration. So the next question you have to ask is this: which of these two reactions, the forward reaction or reverse reaction, will increase the oxygen concentration? And so I think what you can see here is that the way we can get more oxygen is by having some carbon dioxide here breaking down to produce reactants, including oxygen. So if the stress is taking oxygen away, what we're going to do is increase the reverse reaction, and that will allow carbon dioxide to be broken down to create more oxygen gas. Okay? So now at this point it gets, again, a little bit tricky. We figured out that we're going to increase the reverse reaction, but we have to think about how that's going to affect the concentrations of these molecules. Let's think about what happens to carbon monoxide, which is over here. Well, I think you can clearly see is if you have the reverse reaction increase, you're going to get even more carbon monoxide, and so that will go up. Now, what happens to the oxygen? Well, in this example, we're actually taking it away. That is the stress, and so we would expect the concentration of oxygen to go down. And then what happens to the carbon dioxide? Well, if you're increasing the reverse reaction here, then what you're doing is you're going to take away carbon dioxide and it'll form carbon monoxide and oxygen, so that should go down. Okay, let's go on with the next example. Increased temperature of an exothermic reaction. So here we have the same reaction, but what I'm doing is I am indicating that it is exothermic. And so the way I indicate that a reaction is exothermic is I write the energy term on the product side of the equation. This indicates when you go from reactants to products, you release energy into the environment. So we might ask ourselves this question. Imagine increasing the temperature like this. And so here I have this, again, exothermic reaction, and now I'm increasing the energy. So the stress here is increasing the temperature of the reaction and increasing, therefore, the energy in this reaction. How will this reaction respond to the stress? Well, what it's going to do is it's going to either favor the forward reaction or the reverse reaction to take this extra energy away. So you have to think, is it the forward reaction that takes away energy, or is it the reverse reaction? Well, let's think about that. So again, the stress is higher temperature. We have more energy in this reaction. So let's think about this question. If we increase the forward reaction, does that take the energy away? And the answer is no. If anything, that gives you more energy. So that doesn't work. So what we have to do is really we have to increase the reverse reaction. If you increase the reverse reaction, what will happen is that extra energy here, it'll be absorbed by carbon dioxide and it'll be taken away and be used to break it down to carbon monoxide and water. So when, in this example, we increase the temperature of the exothermic reaction here, what we're going to do is we're going to have to increase the reverse reaction to take that extra energy away. So let's imagine what happens to the concentration of these molecules when you increase the reverse reaction. So one thing that happens, as you might expect, if you increase the reverse reaction, here the carbon monoxide will go up, the oxygen will go up, but here, if you're increasing the reverse reaction here, the carbon dioxide should go down. And so here, that's all indicated here. Okay, so now we go through our next example here. We're looking now at a different reaction. This reaction has nitrogen and oxygen as reactants, and now the product is the molecule nitrogen monoxide. And this is an endothermic reaction. The way we indicate that is that we have energy now on the left side of the equation instead of the right side of the equation. So here, this kind of reminds us that for the reaction to go from left to right, what it has to do is it needs to absorb this energy here. And so we have to really include it as a reactant. Okay, so let's get to the question. It says, imagine decreasing the temperature like this. So here we have our reaction. And now if you can imagine this, the temperature is dropping, so we're going to have to take away energy out of the chemical reaction. So we imagine, how does this affect this reaction? So again, we apply Le Chatelier's principle. We say, okay, the stress here is that we're decreasing the temperature, we're taking energy away from the reaction. Therefore, we want to increase either the forward or reverse reaction, which will produce energy into the system. So how does that happen? Well, let's consider going to the forward direction here. What's that going to happen here? Well, if you go to the forward reaction, you're going to have to take energy away. It'll be taken away to form this product here. So here, the forward reaction, what will happen is it'll take even more energy away. You don't want that. But if you favor the reverse reaction, then you create energy. And so the way you handle the stress of taking energy away is, in this case, you favor the reverse direction, which will create the energy. Okay, so now what we have to do is imagine what the effect is going to be on the chemical reaction if we increase the reverse reaction. And so here you can expect, if we increase the reverse reaction here, we're going to increase the nitrogen, we're going to increase the oxygen, but we're going to take away from the product here. And so I have these answers here like this. Okay, so now we're going to investigate how pressure or volume affects a chemical reaction by Le Chatelier's principle. So, but before I talk about this, there's sort of a key point that you need to understand. You need to know the relationship between the number of molecules or moles of a gas and what it has on the pressure of the gas. And this isn't so difficult to understand. So let's look at here condition A on the left side. So here we have a box here. What we have is molecules, and they're moving pretty fast. And what they're doing is they will strike the surface of the box. Well, when these molecules strike the surface of the box, they're putting pressure on the sides of the box. And so you can measure that pressure with some kind of device. And so here the device is recording a value of 5.8. The units to measure pressure, they vary, but here in this picture, we use a unit called atmospheres. You'll learn more about atmospheres later. But now imagine you go to condition B here. And so what I did is I have now 5 times more molecules in this box. And so again, these molecules are moving around and they're striking the side of the box. So they're all moving pretty much at the same speed as before, but now we have 5 times the number of molecules in B. So there are 5 times the number of strikes on the sides of the box. And so we would expect 5 times the pressure. And so that's what you see here. And so the important point here is that if you, for some reason, increase the number of molecules or moles in a system, then what will happen is that the pressure will increase. Okay, so that's one point you need to know. Another point you need to know is you just need to understand that there's sort of an inverse relationship between pressure and volume in a gas in these kinds of Le Chatelier's questions. So what do I mean by inverse? Inverse means opposite. So there's an opposite relationship between the pressure and the volume of the gas. What that basically means is if the pressure for some reason goes up, the volume will go down. If the pressure goes down, the volume goes up. And so we can sort of see that here in considering A versus B. So in A, we have a relatively large volume, and you can see it's a relatively low pressure. But what you can see now in B, the volume is greatly reduced, and now we have a much higher pressure. And so I think you can sort of see why that's occurring, is if you reduce the volume, you will get more strikes per minute on the sides of the box than you had with the greater volume. So if you reduce the volume, that will effectively increase the pressure of a gas. All right, so now we can sort of address how pressure volume affects equilibrium. So let's consider the following reversible reaction. So in this case, we have 2 gases, nitrogen and hydrogen, and they're in a reversible reaction with this molecule, which is called ammonia. That's NH3. And so I say very importantly here, to evaluate the effect of pressure, which is effectively the same as reducing volume, you have to evaluate how many total moles are on the reactant side and on the product side of the equation. So let's look at the reactant side. And so you can see that in this equation, there is 1 mole of nitrogen and 3 moles of hydrogen. So there's a total there of 4 moles. And then on the product side, we only have 1 product here, so there is a total of 2 moles. All right, so there are 4 moles of reactants and 2 moles of products. So here's the key point. If the stress on the chemical reaction is to increase the pressure, or if you decrease the volume, the reaction will respond to decrease the moles. And the reason is, I think you just saw on the previous slide, if you decrease the number of moles in some fashion, you will decrease the pressure. On the other hand, if you decrease the pressure or if you increase the volume, the reaction will respond to increased moles. And the reason is this: if you decrease the pressure by Le Chatelier's principle, you would expect that somehow the reaction might change to increase the pressure, and so we might do that if we can increase the moles. So let's go through this example here. So we have this reaction again, and it says, if pressure increases, how would this equilibrium respond? So what we want to do is this. We have the stress being increased pressure here. So Le Chatelier's principle says that what will happen is that you will either increase the forward or reverse reaction so that you can decrease the pressure. Well, the way you can decrease the pressure is if some fashion you can increase the forward reverse reaction to decrease the number of moles. Decreasing the moles will decrease the pressure. So we have to think about this. Which of these two reactions, the forward reaction or the reverse reaction, will manage to decrease the number of moles? And I think what you can see here is that if you have more of a reverse reaction, you're taking 2 moles of gas and it's becoming 4 moles of gas. And so if anything, that will increase the pressure. We don't want that. So to deal with increased pressure, we increase the forward reaction. And the reason is that'll take 4 moles of reactant and convert it to only 2 moles of product. So we have fewer molecules, the more the reactants are converted to products, and then that should decrease the pressure. So here in this example, if we increase the pressure, what we're going to do is we want to increase the forward reaction because that will reduce the pressure by lowering the number of moles. So what this means is if you increase the forward reaction, what would we expect? We would expect the nitrogen concentration to go down, the hydrogen concentration to go down, right? Because you're taking away with more of a forward reaction. But then if there's an increased forward reaction, we would expect the ammonia concentration to go up. So now what I want to do is give you some more practice here. And so this is more representative of what you're going to see on your test. So here's the first problem. For the following chemical reaction, and so here we have carbon as a reactant and water as a reactant, and we have carbon monoxide as a product and hydrogen as a product. What happens to the concentration of carbon monoxide and water if hydrogen decreases? So if I can decrease the slide. Okay, so let me go ahead and write out the reaction here. So we have carbon in the solid state and reacts with water in the gaseous state, and it produces carbon monoxide in the gaseous state and hydrogen gas in the gaseous state. And so what happens to the concentration of carbon monoxide and water if hydrogen decreases? Okay, so this is what we're doing. The stress is this molecule hydrogen is decreasing. So imagine hydrogen here, you're taking it out of this chemical reaction. And so by Le-Chatelier's principle, we understand that this equilibrium will change, will adjust to somehow relieve the stress. So if the stress is taking hydrogen away, Le-Chatelier's principle predicts that we are going to favor the forward reverse reaction to increase the amount of hydrogen gas. And so the question you need to ask yourself is this. Is it here the forward reaction that increases the amount of hydrogen gas, or is it the reverse reaction? And so what I'm hoping you can see is that here, if you increase the forward reaction, what will happen is that you will get more hydrogen gas produced. And so that should relieve the stress. And so let's go ahead and answer the question. What happens to the concentration of carbon monoxide and water? So we had the forward reaction increasing, and so we might expect that water here will decrease, and then we might expect carbon monoxide for increasing the forward reaction to increase. Okay, so if I can increase the slide. Okay, second question. The following chemical reaction has a change of enthalpy of 131.28 kilojoules. If the temperature increases, what happens to the concentration of water and carbon monoxide? So if I can decrease the slide. Okay, so this is a little bit trickier question to answer because here what we have to do is, in order to answer the question, we really need to introduce an energy term. So you have to ask yourself this question. If this is an endothermic reaction, do we write plus energy on the left side of the equation, or do we write plus energy on the right side of the equation? I'm kind of hoping you know from experience by now, if it's an endothermic reaction, that means as this reaction goes from left to right, it's absorbing energy. And so if it's absorbing energy, you can sort of think of it as maybe as something you add to the reactants to get them to become products. So here, what we need to do is we need to write energy as here on the left side in the reactant side. So now that you've done this, you should be able to answer the question. It says, if the temperature increases, what happens to the concentration of water and carbon monoxide? Okay, so the way I think about it is this. We are increasing here the amount of energy. So the stress is increased temperature, which is increasing the amount of energy. Which of these two reactions, the forward reaction or the reverse reaction, will relieve the stress? Well, if the stress is increased temperature and increased energy, we want to favor the reaction that will decrease the energy. So how do we do that? So I think you can see that if the reverse reaction is increased, you will create even more energy. But if we increase the forward reaction, that should take away the energy from the reactants and stick it into the products. And so what we want to do here is if the temperature increases, we also want to increase the forward reaction, and that should take the energy away. Okay, so now what happens to the concentration of water and carbon dioxide? Well, if you increase the forward reaction, I think you can see you're going to take the water away, so water will decrease. And then if you increase the forward reaction, we should increase the amount of carbon monoxide. So carbon monoxide should increase. Okay, thank you for listening to that, and we'll see you next time.